Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
Welcome to this video on semiconductor contacts, junctions, and the devices which are the basic building blocks of VLSI technology. In a semiconductor device processing, pins and contacts are created using metals. The interface contact of two dissimilar materials are called junctions and the structures as diodes. These devices exhibits properties that are different from their native material layers. The contacts and junctions become part of the device and influence the device performance. In this video we will discuss the properties of materials, contacts, junctions, and device applications. In a metal, loosely bonded valence electrons are liberated and made to conduct in the lattice structure. This electron current flow makes metal a good conductor. Density and mobility of electrons determines the magnitude of current. For example, higher mobility, 1 valence electron silver metal has higher conductivity, as compared to 3 valence electron aluminum. In ASIC processing, metals like gold, copper, aluminum are used to create contacts, junctions, pins, nets, shields, etc. Conductivity of a semiconductor lies between that of a metal and an insulator. The group 4 tetravalent, valence 4 intrinsic semiconductor is used as starting material of ASIC fabrication. The group 3 trivalent or valence 3 semiconductor and a group 5 pentavalent or valence 5 semiconductor elements are called extrinsic materials. The group 3 and 5 semiconductors are used as impurities for doping intrinsic materials. Process of adding impurities or extrinsic material to an intrinsic material is called doping. Adding group 5 impurity to an intrinsic materials results in formation of N-type, electron-rich semiconductor. Similarly, adding group 3 to an intrinsic semiconductor results in formation of P-type, whole majority semiconductor. The magnitude of conductivity of an intrinsic semiconductor is controlled by the doping level and results in formation of N, N+, N++, and P, P+, P++ type semiconductors. From intrinsic silicon atom covalent bonding we observe that there are no free electrons available and hence it exhibits poor conductivity. When an intrinsic semiconductor is doped with pentavalent element like phosphorus, the covalent bond leaves a free electrons that contribute to the conductivity. These negatively charged electron majority carriers creates an N-type semiconductor. When doped with trivalent element like boron, the valence electrons sharing leaves few vacancies known as holes. Thus formed P-type semiconductor will have positively charged majority hole current. The mobility of electrons is higher than that of a hole. In ASIC fabrication, metals are used to make surface contacts on semiconductor surfaces and create electrical connection to devices and nets. These dissimilar materials of different energy bands recombine and form a junction. Thus created junction exhibits electrical characteristics that are totally different from their native materials. A metal semiconductor contact formed by the annealing and etching process is called a silicide. The popular metal semiconductor contacts created are metal with lightly doped silicon, forming a rectifying junction contacts. Metal with highly doped silicon forming a non-rectifying ohmic contact. The conductivity characteristics of a metal-silicon contact depends on the level of silicon doping. A medium or a heavily doped silicon creates an ohmic and non-rectifying contact. The electrical characteristics of a medium and heavily doped silicon contacts are shown in the figure. Thus created ohmic contact has bidirectionally symmetrical conductivity. The contact resistance as shown in the figure depends on the doping level. That is higher the doping, lower is the contact resistance. A P and N-type doped silicon junction creates a potential barrier of about 0.5 volts cut-in voltage. In forward bias, the device offers a low resistance and, in reverse bias, a high impedance. A diode operated as rectifier operates in forward and in reverse blocking state. The reverse breakdown characteristic of a PN junction is controlled by silicon doping level and thereby create avalanche and Zener diodes. These devices are operated in reverse breakdown region and are used as voltage regulator diodes. A reverse biased diode, operating in non-breakdown region, acts as a semiconductor capacitor and is known as a varactor diode. Thus, the diodes operated in different regions are used for different applications. The Schottky barrier contact is made up of a junction of lightly doped silicon and a metal, which creates a significant internal potential barrier. Thus formed Schottky junction diode exhibits asymmetrically conducting ohmic characteristics. The Schottky diode, as compared to conventional diode, exhibits low forward drop, low reverse breakdown voltage and fast switching speed. A typical Schottky PN diode is formed by a junction of doped N-type silicon and P formed by metals like platinum or aluminum. From silicon and Schottky diode parameters comparison table, we observe that, due to heavy doping of Schottky diode, it exhibits lower forward drop, low reverse breakdown voltage, higher reverse leakage current and fast switching speeds. Low forward voltage drop results in lower power dissipation and hence makes it most suitable for high-frequency rectification in applications such as SMPS, converters, etc. The low forward voltage drop makes it suitable for reverse polarity protection, clamping diode, surge suppression diode. Thin insulating layer sandwiched between two conductors creates a tunnel contact. In this structure carriers follow quantum mechanical tunneling phenomenon, wherein carriers directly pass through thin insulating layer. Forward voltage increase to peak voltage results in increase to I peak current. Between V peak and V valley, the device enters into negative resistance region and current reduces to I valley. Further voltage increase beyond V valley results in current increase. Thus base the biasing operating point determines the region of operation. Tunnel diodes are used as switch, amplifier, oscillator, RF applications, etc. The table shows a typical data sheet of a tunnel diode. It specifies the forward biased operating peak and valley, voltage and current parameters. It indicates the device forward voltage drop at rated current and also indicates series resistance and capacitance parameters. A varactor is a semiconductor diode variable capacitor, also known as varicap. The diode reverse bias variation causes variation of depletion region width, which in turn causes the diode capacitance variation. Varactor diodes are typically constructed using semiconductor materials like silicon or gallium arsenide. They are widely used in tuned RF filter circuits, voltage-controlled oscillators, voltage-controlled delay lines, harmonic generators, etc. Table shows varactor diodes data sheet indicating maximum ratings and electrical parameters. Varactor diode is operated in reverse bias condition and the data sheet indicates reverse leakage current, breakdown voltage. It also indicates the assured maximum to minimum capacitance variation ratio, minimum capacitance value, the Q factor, etc. Contact parasitic resistance impact issues are signal degradation, limiting of current transients, Joule heating, contact thermal expansion, mechanical pressure exerted on die, etc. The electromigration issues result in open contacts. All the above issues will lead to the degradation or the catastrophic failures that lead to reliability issues. The device parasitic capacitance along with the Terminal parasitic contact resistance forms, parasitic RC delay time constant. This delay at various terminals reduces the transient or dynamic response, speed, or frequency response of the device. The drain-to-gate parasitic capacitance gets magnified by GM times, and that coupled with parasitic resistance, causes large delays. Thus terminal parasitic will deteriorate the performance of the device. Junctions created with different materials and characteristics result in formation of wide range of diodes. These devices sensitive to inputs parameters like electrical, light, temperature etc., realize different functionalities. Some of the other devices are photodiode, light-emitting diode, surge suppression diode, fast recovery diode, laser diode, Skoclay diode, clipping, clamping diodes, and so on. Thanks for your time. Hope to meet you in upcoming video. Bye for now.